Hi everyone, my name is Ainalis, and today I'm going to present some work we've done recently on a national framework to assess electric road systems and present some results from our UK case study. So our ERS feasibility study funded by Innovate UK was led by Costain and involved members from the SRF, Siemens, Scania and other companies listed below. The aim was for us to deliver this feasibility study and a system demonstrator program for zero emission HGVs using an ERS. The total project costs were £2 million and it was funded at 1.2 million. And the project lasted for 9 months from July 21 to March 22. There were 9 work packages, and today I'm going to focus on work package 4, which is system-wide considerations. So work package 4 was focused on designing what a final system and rollout would look like across the UK. So the main research questions that we tried to answer were, can we understand the reality of UK logistics? What is the optimal length of an ERS network versus battery size versus static charging configurations? And what I'll discuss in detail today is about developing economic and environmental national models to assess this. So now I'm going to discuss a little bit about the national case and rollout and the model that we developed and the input data that we've assembled to feed into this model. So in having a model to understand the economic and environmental impacts for decarbonising HGVs, we looked at different technology pathways across the time period 2025 to 2050. And this focused on diesel as a baseline in the current dominant powertrain, along with ERS and battery electric HGVs and hydrogen fuel cell vehicles. And the main aim was that any new HGV needs to reach parity with diesel within the vehicle's first life. And if this wasn't achieved, then there needed to be government intervention. And conversely, if it achieved it before the vehicle's first life, then there was an opportunity for revenue to be sought by the government. So for this national model, we gathered a series of input data from 2025 all the way out to 2050, and this was used to predict the hydrogen infrastructure costs for generation and storage, and then we can predict the production fuel costs of the hydrogen. We also had some battery electric vehicle electric road system infrastructure costs and used some fixed electricity costs. We also had a national fleet model that dictated the uptake of and replacement of diesel trucks with zero emission vehicles, and then determine the total energy consumption and required infrastructure build out needed. We then had a fleet operator model that looked at the vehicle total cost of ownership for the 3 powertrains mentioned, and this includes the vehicle financing, the fuel costs, maintenance, any depot supporting infrastructure and supporting operations needed. From this total cost of ownership, we could work out what the fuel costs and subsidy costs or revenue costs were needed for parity with diesel. And on the ERS side, this included a margin charged on top for using ERS electricity. And then finally, we combined all these costs together to perform an economic and environmental comparison at a national level. So some of the input data that we gathered for the national model was the baseline fuel prices, where we selected some typical values currently used, things like diesel and electricity, and used some gas prices to infer a blue hydrogen price. Typical fleet operators, where we profiled the operations in terms of vehicles and mileage, the vehicle specifications and the related costs, and also for the depot infrastructure. For the ERS, we had the capital costs for construction, the operating costs and the electricity margin, and we used a build-out profile that built out an initial system that was then upgraded later on once the number of zero-emission vehicles reached a critical number. For the green hydrogen, we looked at the generation, compression, transport, and storage, and this included the efficiency of the process and the infrastructure costs, and this gave us a production fuel cost for hydrogen from 2025 out to 2050. In terms of the national inputs, we had the emissions intensities and also the vehicle uptake and replacement rate. And this chart here shows the vehicle zero emission vehicle park of HGVs in the UK from 2025 to 2050. So now I'm going to present some of the results for the UK that we've generated. First, let's look at the total cost of ownership from a fleet operator's perspective. So this is a snapshot of the total cost of ownership at 2030 over a 6-year first life, and comparing in order diesel, 4 different battery electric vehicles with different battery capacities from 150, 300, 500 kilowatt hour and a 1.2 megawatt hour big battery vehicle, and green and blue hydrogen powered fuel cell vehicles. And what you can see is at 2030, the battery electric vehicles with the smaller battery capacities actually cost less to operate compared to the current diesel vehicles, while the large battery electric vehicles and the fuel cell vehicles are much more expensive to run. And so this means that they will need to be subsidized in order to meet parity with diesel, whereas the small battery electric vehicles have some headroom to be able to generate revenue for the government. And if we step forward to 2040, we can see a similar thing happening where the 500 kilowatt battery vehicle has a lower cost than diesel, and the smaller battery electric vehicles have even better total cost of ownership compared to diesel. However, the big battery vehicle and the hydrogen fuel cell vehicles, even by 2040, are still more expensive than current diesel operations. And so what does this mean now from the total cost of ownership to looking at that parity and if there's a subsidy required in order to ensure that the operations meet parity with diesel? So if we look at hydrogen, you can see that for most of the periods, there's a large subsidy that needs to be provided all the way out to 2050 because of the higher operating and capital cost of running hydrogen vehicles. And this is particularly for the green hydrogen, which starts out quite expensive. You need to provide a really high subsidy, over £4 per kilogram in 2025 to meet parity with diesel. And this closes down, but by 2050 you still need to provide a subsidy in the order of £1 per kilo in order to meet diesel parity. If we look at the battery electric ERS vehicles, you can see that parity with diesel can be achieved depending on the battery capacity that's installed on the vehicle quite early. So by 2030, both the 150 and 300 kilowatt hour vehicles are cheaper to run, and then this means that you can provide revenue to the government on the electricity without compromising that operating cost compared to diesel. The large battery electric vehicle doesn't have a point where it becomes cheaper, and so that will also need to be constantly provided with a subsidy to keep that parity. So now we can take these vehicle subsidies and scale them up to a national level and look at what the impact would be on either solutions from hydrogen to ERS battery electric vehicle. And so we've got some costs here to build and upgrade the ERS. We've got some ERS usages and the electricity margin and base retail price. And we've also looked at 2 different wholesale electricity prices for green hydrogen. You've got a blue hydrogen green hydrogen at 5p per kilowatt hour and at 12p per kilowatt hour, and the 3 battery electric vehicles with battery sizes from 150 up to 500 kilowatt hours. And what we can see here is that there's a potential, if the electricity price is high, for green hydrogen to require a huge subsidy from the government to maintain parity with diesel. Whereas on the other hand, a combination of ERS with battery electric vehicles, even with the additional capital costs up front, there's more potential to generate revenue and reduce the required subsidy. And if the batteries are small enough and the vehicle costs are small enough, actually generate some revenue for the government. And if we look at another case where we've increased the cost to build and upgrade the ERS, we can still see that despite the government having to subsidise most of the options, there's far less subsidy that needs to go into smaller battery electric vehicles and an ERS than there is for green hydrogen or even blue hydrogen. And so just to give you an example of another way we can use this model is we can compare it with the break-even wholesale electricity price for green hydrogen to work out what our ERS lane kilometre cost targets need to be and what that boundary is. So if we look at 5p per kilowatt hour, you can see that the target costs for an ERS lie somewhere in that range. And this is depending on different lane kilometers that you build. So as you go from the green triangles to the blue circles to the red squares, you're building more and more ERS. So your margin for the target lane kilometer cost goes down. And finally, just a comparison of the annual emissions. So we've got the CO2 emissions in megatons over time from 2025 out to 2050. And if we look at diesel, which is the black dashed line in the middle, that's a business as usual case. But if we look at the potential for grey hydrogen, the high and low pathways, it falls around and far above what the current diesel is. So it's somewhere in that grey shaded region. And that shows that grey hydrogen, could be marginally better, but is more likely to be much, much worse in terms of emissions. Blue hydrogen can be around as good as current diesel emissions, but can provide some reduction somewhere in this blue shaded region. The green hydrogen can provide some reductions, but depending on how much energy and where the energy is coming from, there's a bit of a variation there, and it may not reach zero emissions. The ERS pathway, so if we take a sort of mid-range case, we've got some high and low pathways there, but there's a very small shaded region there. But so the ERS can provide as good as sort of the best green hydrogen, if not better. So just to wrap up, we completed our feasibility study on an ERS in the UK. We developed a framework and model at a national level that takes into account economic calculations from fleet operator and national perspective, and also the environmental emissions, both embodied and fuel. We were able to develop a method using this model to identify the system cost limits for the economic feasibility of an ERS compared to hydrogen for HGVs. And so in the future, we're going to continue using this model to look at a full range of sensitivities and regions. We're going to extend the embodied emissions to include hydrogen infrastructure. And as we continue to gather new data, we'll refine the costs and inputs as we go on. So I just wanted to say thank you for listening, and I should be around to answer any questions.